Today we're going to talk about subdividing a segment in a given ratio, which is going to be exactly what it sounds like. So the big idea today is something called partitioning. So if you've never heard this word before, here's the definition of it. To partition a segment means to divide it into two segments with a given ratio. So let's look at some examples of partitioning. Here are some examples of one-to-one partitions where essentially we have equal parts. You see we have the sawing the lady in half, we have the house divided, and the sandwich is cut directly in half where they're two equal parts. You can think about this being like the midpoint being found on a segment and kind of cutting it where it's two equal parts. But that's kind of a special case. Most of the time when you're subdividing using a ratio, it's going to be something else besides just cut it in half. Here are examples of looking at 2-to-1. So we have three total parts, right? I have 1, 2, 3 parts of my flag. 1, 2, 3 parts of my flag. I have three triplets, right? But we're separating the segments into be two parts. So if I were to maybe shade in these two parts of the flag and say 2-to-1, right? If I were to say, all right, these two triplets and this one triplet right here, right, where I have 2-to-1, is how we could partition. Here's an example of 3-to-1. So we have, in this case, 4 total parts. And another key thing I want to look at right here, you may see this semicolon here. That's another way of writing 3-to-1. It's very common in terms of ratios if you haven't seen that before. We have 4 total parts in this case, and 3 are on one side. Got the 4 square right here. If you've ever played 4 square, it's kind of like if you're in the king square and you're against everyone, you're the one person versus all 3 others trying to get into that king square. All right, so let's look at some examples where we're going to use this in this class. But that's partitioning in a nutshell and where you've seen that in real life with different things. Here, we're going to use this mostly for finding segments when we're given a ratio. In this case, I don't have the ratio, but I'm going to try to figure out what it is. So how is xz partitioned in terms of x, y? So in this case, xz is right here, right? This part, xy being the total, the whole thing, if I were to go from all the way from x to y. So how long is xz in terms of this entire segment? So what we're going to do here, we're going to figure out, well, the slope from x to y is we got 3 to the right, 6 up. So let's figure out how far do we have to go to the right to get to z. So I'd say 1, 2, 2 over, and that'd go up 1, 2, 3, 4. So I have kind of another mini triangle in here where it's 2 to 4. So to figure out what the ratio of this is, I'll take 2 over 3 and then 4 over 6, where I'm finding 4 and 6, 2 and 3, kind of comparing those two. So in this case, it looks like it is a 2/3 ratio where xz is 2/3 of xy. So we'd say the ratio in this case is 2 to 1. Now, why did I not say 2 to 3? Because I have essentially 2 parts of the entire xy is represented in xz, and I have 1 part represented in zy right here. So total, we have 3 parts, and we have 2 of them are being represented by xz. So when you see this is read as 2 to 1 as well. So let's look at some other examples. So in this case, I'm going to kind of start from scratch and figure out I want to partition CD into a 2-to-1 ratio. So kind of going the other way, we're given the ratio. Now we want to actually figure out, well, where is this point going to land on CD. So we'll start by finding the coordinates of C. So it looks like that's at -4, -4 for the coordinates of C. And then we got the coordinates of D, look like they're at 2, 5. All right, so I got those. The rise from C to D looks like I'm going from -4 on the y-axis to +5, so I'd say 9 units. So it's like from C to D would be 9. Kind of a little squiggly there at the end. From the run, right, we're going to rise and then run to the side, so that would be from -4 over 2, so it'd be 6. So we got our run is 6. with a 2-to-1 ratio, we're going to move blank amounts of the rise and blank amounts of the run. So we're going to make it similar to our last one where we have 2-to-1 means there are 2 plus 1 total parts, and we're trying to go 2 of them. So this is how I set my ratio. I got 2 plus the 1 goes in the bottom, so it's a 3 total parts, and we're looking at trying to go 2/3 of that to make that a 2-to-1 ratio. So what I would do, I would say move 2/3 of the rise and 2/3 of the run to get to the point of partition. It tells me where I'm going to kind of split this thing up. So in this case, all you do is you just multiply each the run and the rise by 2/3 to figure out what that is. So a little quick demo on multiplying fractions. You just make it over 1, 6 over 1, and this would be 12 over 3, 6 times 2, 3 times 1, right? You multiply across the numerators and across the denominators. That gives me 4, which makes sense. 4 sounds like about 2/3 of 6. Should be smaller, not bigger. So I'd go over 1, 2, 3, 4. So I know I'm going 4 right here. And then let me just do a different color. So I'm going 4. And then for 9, I'd say make that 9 over 1. So it'd be 18 over 3. So it'd be 6. 9 times 2 is 18. 1 times 3 is 3. So that'd go up 1, 2, 3, 4, 5, 6. So I went over the right 4 and then up 6. So I land, looks like at the point 0, 2. So I went ahead and already kind of hopped to the finish line here. So I landed at the point 0, 2. We'll call that X. One of the markers, the coordinates of the point partition are 0, 2. So I should put that there. We added blank to the X coordinate of C. So we added 4. And then we added 6 to the Y coordinate to get the point of partition. All right, look at 2 or 3 more examples. So here we're given endpoints and we're given the ratio. We're trying to figure out, okay, where is Q going to be on this line? So we'll go ahead and plot these points, -4, -2. And then I got for A, and then for B, I got 1, 8, B, B right there. All right, let's try our best line here. Something like that. So we'll say my ratio is 4-to-1. Okay, so in this case, I'm going to have my denominator for my ratio is going to be 4 plus 1 because I'm going to have in total 5 parts. And I'm looking to make it a 4-to-1 ratio, so we'll just make it 4 on the top. So in this case, my ratio is 4 over 5. So what I'm going to do here, I'm going to find how far over a slope from A to B, and then I'm going to multiply that, each one of those X and Y by 4/5 to figure out how far we go. So we'd say, let's see, my slope from A, my rise, I go from -2 to 8 is going to be 10. So I got 10, and then my run would be, looks like 1, 2, 3, 4, 5. I believe from -4 to 1. That sounds right. So I got 10 over 5 is my rise over run. So to figure out what's 4/5 of that, I'm going to multiply 10 times 4/5 and 5 times 4/5 and see what we get. So 5 times 4/5, that's going to be 20 over 5, which would be 4. So I'm going to go 4 to the right. And then 10 times 4/5, that's going to give me, let's see, I can reduce that down to say 5 goes into 10 2 times, 5 goes into 5 1 time, so that'd be 2 times 4 would be 8 over 1. You don't have to reduce down. It's kind of a trick there to make it a little bit easier when multiplying fractions. I got 8. So let's see. So now I'll say I go to the right 4, 1, 2, 3, 4, and then I go up 8. So it lands right here at the point, looks like 0, 6. Or that right there. Oops, I drew an extra parentheses. They're already there. But 0, 6. So that would be how you attack that problem. Now looking at one more example. Let's see, we got